Fisher's linear case and the Eisenberg-Gale convex program. Fisher's linear case is the following. Consider a market consisting of a set B of buyers and a set A of divisible goods. Assume the size of A equals to n and the size of B equals to n prime. We are given for each buyer I the amount EI of money she possesses, and for each good J the amount BJ of the good. In addition, we are given the utility functions of the buyers. Our critical assumption is that these functions are linear. Let Uij denote the utility derived by I and obtaining a unit amount of good J. Thus, if the buyer I is given Xij units of good J for 1 less than equals to J less than equals to N, then the happiness she derives is the summations of Uij times Xij summing starting with index starting from 1 to n. Prices P1, P2, P3, and Pn of the goods are set to be market clearing prices if, after each buyer is assigned an optimal basket of goods relative to these prices, there is no surplus or deficiency of any of the goods. Our problem is to compute such prices in polynomial time. First, observe that without loss of generality, we may assume that each bj is unit by scaling the uij's appropriately. The uij's and ei's are in general rational. By scaling appropriately, they may be assumed to be integral. We will make the mild assumption that each good has a potential buyer, i.e. a buyer who derives non-zero utility from this good. Under this assumption, market clearing prices do exist. It turns out that equilibrium allocations for Fisher's linear case are captured as optimal solutions to a remarkable convex program, the Eisenberg-Gale convex program. Before stating the program, it will be instructive to list the considerations that would be useful in deriving such a program. Clearly, a convex program whose optimal solution is an equilibrium allocation must have as constraints the packing constraints on the xij's. Furthermore, its objective function, which attempts to maximize utilities derived, should satisfy the following. If the utilities of any buyer are scaled by a constant, the optimal allocation remains unchanged. If the money of a buyer B is split among two new buyers whose utility functions are the same as that of B, then sum of the optimal allocations of the new buyers should be an optimal allocation for B. The money-weighted geometric mean of buyer's utility satisfies both these conditions. The maxima taken of the term, the multiplications of ui to the ei for all I in A to the exponent 1 over the summations of ei summing for all E. Clearly, the following objective function is equivalent. That is, we take the maxima of the multiplication of ui to the ei for all I in A. Its log is used in the Eisenberg-Gale convex program. Maximize the summations of ei log ui summing with I index I starting from 1 to n prime, subject to ui equals to the summations of uij xij, summing with index j starting from 1 to n for I in B, and another subject is the summations of xij summing with index I starting from 1 to n prime is less than equals to 1 for all j in A, and xij is greater than or equals to 0 for all I in B and for all j in A. Where xij is the amount of good j allocated to buyer I, interpret Lagrangian variables, say pj's, corresponding to the second set of conditions as prices of goods by the Hirsch-Cohn-Tucker KKT conditions. Optimal solutions to xij's and pj's must satisfy the following. 1. For all j in A, pj is greater than or equals to 0. 2. For all j in A, pj is greater than 0, which implies the summations of xij, summing for all those I in A, is equals to 1. 3. For all I in B, for all j in A, uij over pj is less than or equals to the summations of uij xij, summing for all those j in A over ei. For I in B and for all I in B and for all j in A, xij greater than 0 implies uij over pj is equals to the summations of uij times xij, summing for all those j in A over ei. From these conditions, one can derive that an optimal solution to convex program 5.1 must satisfy the market clearing conditions. The Eisenberg and Gale program also helps prove in a very simple manner the following basic properties of equilibria for the linear case of Fisher's model. Theorem 5.1. For the linear case of Fisher's model, if each good has a potential buyer, equilibrium exists. The set of equilibrium allocations is convex. Equilibrium utilities and prices are unique. If all uij's and ei's are rational, then equilibrium allocations and prices are also rational. Moreover, they can be written using polynomially many bits in the length of the instance. Proof. Corresponding to good j, there is a buyer I such that uij is greater than 0 by the third KKT condition. Pj is greater than or equals to ei times uij over the summations of uij times xij, summing for all j, and such term is greater than 0. Now, by the second KKT condition, the summations of xij summing for all I in A is equals to 1. Hence, prices of all goods are positive and all goods are fully sold. The third and fourth conditions imply that if buyer I gets good j, then j must be among the goods that give buyer I maximum utility per unit money spent at current prices. Hence, each buyer gets only a bundle consisting of her most desired goods, i.e. an optimal bundle. The fourth condition is equivalent to, for all I in B and for all j in A, ei times uij times xij over the summations of uij times xij summing for all those j in A is equals to pj times xij, summing over all j gives for all I in B, ei times the summations of uij times xij summing for all j over the summations of uij times xij summing for all j in A is equals to the summations of pj times xij summing for all j. This implies for all I in B, ei equals to the summations of pj times xij summing for all j. Hence, the money of each buyer is fully spent. This completes the proof that market equilibrium exists. Since each equilibrium allocation is an optimal solution to the Eisenberg-Gale convex program, the set of equilibrium allocations must form a convex set. Since log is a strictly concave function, if there is more than one equilibrium, the utility derived by each buyer must be the same in all equilibria. This fact, together with the fourth condition, gives that the equilibrium prices are unique. Finally, we prove the fourth claim by showing that equilibrium allocations and prices are solutions to a system of linear equations. Let qj equals to 1 over pj be the new variable corresponding to each good j, and let k be the number of non-zero xij's in an equilibrium allocation. The system will consist of k plus l equations over k plus l unknowns, the latter being the n qj's, and the k the non-zero xij's. Equations are corresponding to each good j the equality given by the second kkt condition, and corresponding to each non-zero xij the equality given by the fourth kkt condition.